All right. So today is March 31st, and we're nearing the end. So we're going to finish up the standard template library today, most likely, and then next class we'll do exceptions. And then the final class on Monday will be um, a review, or like a working through the practice exam. I haven't figured out exactly what we'll do, but so tutorial 6 is due this weekend, and so today, the stuff we're going to learn today is going to give you the tools you need to complete it. I mean, you can just try it on your own. There's plenty of ways to get it done. Assignment 4 is due. Now, I didn't realize when I pushed that back that that was Easter Sunday, so I think I'm going to extend it to the last day of classes. All right, so assignment 4, well, let's say the sort of official deadline is Tuesday night at midnight, but the unofficial deadline is 8 a.m. Wednesday. Right, so I mean, I've not officially changed anything, but that's what I'm going to move it to, just so people can enjoy their Easter. And it's auto-graded, so there's not really, I'm not putting anybody out by doing that. So yeah, questions? Okay. Last class, we were talking about the standard template library, so we're going to continue doing that. Now, in terms of how much of this stuff is going to appear on your final exam, well, some of it. Iterators, this stuff, for sure. Right, you should know basic iterators, and you should know sort of the fundamental differences. We're going to focus a lot on list and vectors. You should know the difference between those two types of iterators. And so, when in doubt, just kind of treat it like a pointer. So last class, we were talking about, well, how do we access list elements, right? So our doubly linked list. So for a vector, we have like the at and we have the subscript. For a doubly linked list, we did not have the subscript. I don't know if it has an at. I don't know, I'd have to check. But one way to access elements, in an arbitrary sort of order in a linked list is to use iterators, right? And so I'm sort of bound to how linked lists do traversals. That is, my iterators, I cannot use random access like I do on a vector. Actually, we're going to see that shortly. But we can walk forwards and through and backwards through the list. So we have forward iterators, and dot begin gives me the iterator that points to the first element, and dot end gives me an iterator pointing to just past the last element. Yeah, and then you can do all that stuff in reverse as well. So there's these categories of iterators. Now, I probably mentioned this. I think this part might be a little bit of review, but I don't know the difference between these two iterators. I mean, I've looked for instances where I would use one category but not the other, and to me they seem basically the same. I don't know what other containers other than streams would only work in the forward direction, a singly linked list, I guess, if you chose to implement one. But certainly, I don't know if you would find anything in the standard template library. Maybe, but regardless, so we're going to look at an example of these types. The linked list that we just looked at is a bidirectional iterator, which means that we can walk forward and backwards. And random access is the most powerful type. This is what we get with a vector. We can do things like pointer arithmetic and subscripts. So each of these categories contains all the abilities of those above them, but the syntax is the same, right? Except for, you can't use subscript on anything other than random access, but the dereferencing and the increment, those all work the same. So yeah, this is sort of stuff that we just talked about. Basically, the iterators are based on the underlying collection type, right? So iterators are an abstraction, but they're a leaky one. You can kind of you kind of have to know what you're dealing with underneath it in order to properly use them. So all iterators support these, the dereferencing, and I would add to that the arrow operator. The increment, the assignment, of course, I can make an iterator variable and assign it a value. And I can test to see if two iterators are equal or not equal. In addition, forward bidirectional and random access support these function calls, right? So I can get instances of iterators. We're going to actually, the first thing we're going to look at is stream iterators, which do not have these function calls. Bidirectional and random access also support going backwards through my list and the decrement operator, right? So those are sort of logically the same. And then on top of that, random access supports the subscript operator and also relational. So that's kind of important, right? So if I have two iterators on a vector, I can ask which one is greater than the other, and it will return true or false. If I have two iterators on a linked list, I cannot do that, right? Because I don't know. Like, yes, I know when I grab the iterators which order they were in, but if you just hand me two iterators and say what order they were in, and they're in a linked list, then there's no way for me to know other than traversing the entire list, right? So there's no easy way to implement these relational operators outside of a random access collection class. And then on top of that, of course, we can do pointer arithmetic. We can add or subtract indexes from iterators. For optimal performance, use the prefix increment and decrement, right? We saw why that is better. Outside of, sometimes your compiler will optimize these things. One thing we didn't do, so this, when we wrote our for loops, we did something like this: for it equals list.begin. And then we said it not equal to list.end. Well, this function only gets called the once, right? That's how we initialize it. But this one gets called every loop. So that's not really the most efficient way to do that. Rather than calling this function every single time, I should store it in an iterator, right? Like maybe an end iterator, and then compare my current iterator with the end iterator, and that will save me some function calls. All right. So those are iterators. The other part of the STL is the containers. So containers, basically, they're data structures. That's what they are. They all have the same data type up to inheritance, right? Because they can all be holding animals, but I don't maybe know what particular type of animals they are. The types of containers are sequence, associative, and container adapters. So we're going to see examples of those. But basically, I think we go over that in detail later, actually. So all STL containers provide default constructors, copy constructors, right? I can actually make a copy of them. Destructor and assignment operator, right? So the copy constructor and assignment operator are going to do a lot of work if you call them, right? They're going to go through and copy all the elements inside your container. We also have these functions for sort of modifying these containers: insert, delete, and clear. We have some size-related functions and relational operators, right? So I can tell which container is greater than or less than another container. They use lexicographical order, which, if you're wondering, is like alphabetical order, right? When I compare two words, I don't compare two words as a whole. I look at the first character. I see if one is greater than the other. Then, if one starts with A and the other starts with B, then the one with A starts first, regardless of what the rest of it looks like. And so when we look at containers, we do the same sort of thing. We look at the two first elements, right? Let's say we had two lists of ints. Sure. And now which one of these is less than the other? Well, we're going to go through and we're going to compare them one by one. So we're going to look at the first. Actually, let's change this to this. We'll look at the first element. Well, those are equal, so we can't tell from there. So we're going to look and compare the next element, and we're going to see that 6 is less than 7. That means if this is L1 and this is L2, That means L2 is less than L1, and I don't even have to look at the rest of the list, right? So that's lexicographical order. It's the same as alphabetical, but more generalized. I can apply that to any data type that implements a less than operator. All right. If we are making things that we want to store in these containers, we should keep in mind that many copies could be made, right? We've seen that with the vector storing the student class. And if so, if we have something that, for instance, has dynamic memory, in other words, we want to do a deep copy, then we should make sure that we overload these, the copy constructor and the assignment operator. And if we want to do things like sorting or finding, then we should make sure that these operators are also overloaded. You don't necessarily need this. You can pass in arbitrary functions, as we'll see, but by default, it's going to rely on those. All right. Let's look at streams as containers. All right, so we're going to take what I think is, I mean, a lot of people hate the OStream library and how we sort of handle. I mean, they're moving back to, what is it called? Printf or whatever. So people like printf better. And in the latest version of C++, that's what they're moving back to. But I kind of think this is sort of elegant. At least I have no major complaints about it. But what we're going to do is we're going to take this elegant method of outputting strings to the console, and we're going to make it look pretty ugly. So we're going to wrap iterator. Now these are templates, so it's going to be on strings, right? So this means that this particular iterator will accept strings to send to the standard output. We'll call it the output iterator, and we're going to pass it as an argument, the standard output. All right, so what can we do with this out iterator now? Well, it's an iterator, so I want to assign it, I want to basically write strings to the console. To do that, if I dereference it, that should give me back the next string. And so I can say, assign that a value, hello world. And then let's advance it. And then let's say, hello again. No, I'm good, I think. All right, hello world, hello again. So that's what I can do. Now this is like, as far as I'm concerned, this is like really awkward compared to like, why would you do this? But outside of why, which is, well, there's a few reasons why, because we can use algorithms from the algorithm library on this now, and which means that we can sort of take containers and sort of like copy them to the output stream, but maybe do so in a way that filters it at the same time. There's lots of stuff we can do with this. This is sort of allowed, but I don't know if I would ever want to do this. One thing I can't do here is send, right? Even though this is sort of an output stream iterator, it does not accept this end line argument, right? So it's looking for an operator that'll do this, but there is not one. So if I'm going to do this, I need to do the old-fashioned method from C of just manually putting in my new lines. All right, so hello world, hello again. Now, as it turns out, there is some discrepancies here. I don't actually need to do this, right? I put it in because syntactically the compiler will accept it, but in terms of actual use, it does not matter. I don't need to advance the output iterator. The reason being, once I send this to the output, like I can't take it back, right? I can't walk backwards through the things that I've sent to the console. This is gone. Once this operation is complete, I don't have access to it anymore. So This, like advancing the iterator, makes no sense. All right. Well, let's do an input stream. So let's do, here I'm going to say, please input 2 strings, exclamation mark. All right. So now let's make an input stream iterator. I'm just going to steal this. Change this to an I stream. Change this to in. And change this to cin. Okay. And now what I want to do is I'm going to declare 2 strings, string 1 and string 2. And I'm going to grab some strings from the input stream. So I want to say cr1 equals dereference, right? This is technically an iterator, but if I dereference it, I get back a string. And then I can assign that string to str1. And then I can do the same for str2. And then I can do, oh, this is such a pain. You entered str1 plus, and okay. So now it should be able to say hello world, prompt me for 2 strings. I'm going to enter them and it's going to read them back, presumably. So I'm going to say hello there. And it says you entered hello and hello. All right. So we've come up against basically the fundamental difference between output streams and input streams. For an output stream, this line doesn't matter. But for an input stream, it does. So here I am reading the next token off my input stream. Now recall these are separated by default, they're separated by any white space or new lines, right? So hello there, I left a space that gives me 2 separate tokens. I have to, but it's still sitting on the input buffer. So I have to advance the buffer and say like, throw away that token and let's move on to the next one. So I'm going to say plus plus in iterator. And then that should advance it. Hello there. And you, oh, what did I do? I did not save it. And I did not put a semicolon. Hello there, and now it says you entered hello in there. All right, so for the input stream iterators, it's a little more picky. You do have to advance it. And also, I believe, I don't think you can get away with this. Yeah, it does not like that whatsoever. So, oh, yeah, I didn't show you that part, eh? So for the input stream, I have to dereference it. For the output stream, it allows some really lax syntax. That still works, right? That hello world, I sent a string to an iterator and it printed it to the output stream, which I don't really like. I mean, whatever, it's not, there's people smarter than me who made the language who decided that's okay. So they probably have some very good reasons, but to me, this is deceptive because if I'm reading this, now I think this might be a string, right? Out iterator. Whereas if I dereference it, then I know it's not a string, and then I can maybe take a guess that it's an iterator. So in terms of readability, I like this a lot more, but the compiler is really not picky about how you do that there. But on the input streams, it is. But yeah, all right, questions? Okay. Oh yeah, one more thing. So what do I mean, we didn't do anything particularly interesting there, so let's do something a little more interesting. We're going to make a vector of strings, and then we're going to have this little string here just to read from. We are going to tell the user to enter words ending with end. We're going to make an input stream, and then we're going to start reading from that, or input stream iterator. And then we're just going to keep reading. Basically, every loop, we're going to read another one until we reach end. And until we reach end, we're just going to keep pushing back onto this vector. And then once that is done, we're going to make an output stream iterator. And we're going to, well, I have a vector now, which is a container, and it has iterators, and I have an output stream, which is, you can think of as a container with iterators. And so I'm going to use a function from the algorithms library, which I've included, called copy, to copy from one set of iterators to another, right? So I'm going to copy, and it's called words. So I'm going to copy from words.begin up to words.end, which is the entire vector, and I'm going to copy that to the output stream iterator. And all right, yes, we don't need that. So hi there, how are you? And it prints the words, hi there, how are you? A little problem with the formatting. So that's pretty ugly. There may be, right? So if I do something like this, typically, well, I can use it for the output stream, but maybe I would use it for a file stream or something like that. But let's say that I wanted to, I don't like this formatting, so I want to add a little bit of formatting. When I create my iterator, I'm going to say, well, every time you output something to this iterator, then please output this in addition to that, right? So it's going to have, in some sense, a built-in delimiter now. So hi there, whoops. And then when it prints it out, we have spaces now between our strings. I'm not limited to spaces, of course. I can do other things like an asterisk. And then it inserts an asterisk in between each word. Well, not quite in between, but like after each word. So it acts as a delimiter, but I get an extra one at the end. Yeah, so that's sort of one use for it. Again, you typically wouldn't use that with the console, but you might. But maybe for like reading and writing to and from files, this might work very well. Questions? Okay. Yeah, so all right. We've already talked about these things more or less. Okay, so sequence containers are containers that retain the order of the elements. So types of sequence containers, vector, list, and deck. And when we say order, I mean associative containers also maintain an order, but in this case, it's the order that we impose, right? We can say insert something in the second location, and then that thing is at location, 1, if I start counting at 0. I can also do things like grab the front or the back, or I can push and pop from the back. The vector, we have covered this, I think, enough, right? Essentially, there's a backing array. As I add things, that backing array grows. It grows by doubling every time it runs out of room. That's essentially the gist of that. The implication is that we're going to make a lot of copies of things. So yeah, let's take a look at our vector, and then we'll take a look at the linked list. So yeah, we just want to demonstrate a couple things. This is essentially the same thing we were doing before. I have a vector of words, and I'm going to write those words to the output stream using the copy function, and then I'm going to call this capacity thing. Now, if we remember, yeah, I think that's fine. Nothing to be done. Okay, so hi there, how are you? End. Now, I've written 5 words here, which means that the first one, it's going to give me a backing array of size 1. And then when I try to add there to the vector, it's going to double the size of the backing array to 2. When I try to add how, it's going to double it again to 4. And then it'll have space to add r. And then when I try to add u, it's going to double it again to 8. And so here I just output all of the strings that are on my vector. And if I look at the capacity, it says it has a capacity of 8. So if I want to know the size of my backing array, I can use this call to capacity, right? It's different from size. I do not have 8 elements in this vector. This is strictly how much can I contain before I have to grow again. All right. Well, this copy function, again, as mentioned, it is, we didn't do it yet. So we will probably get maybe at the end of class. I have to hurry to get there, but. So before we copy things to the output stream, but here now I declared a second vector called words2. I passed in a value, words1.size. And what that's going to do is it's going to make a backing array of that size, right? So if I put 5 words in words1, it's going to initialize words2 with a backing array of size 5. And then I'll be able to copy everything from words1 into words2. Once I'm done that, I can copy words2 to the output stream. In other words, I'm going to print it. Okay, now that would have been useful if I remembered. Regardless though, I did manage to copy these 5 words into words2. I did also want to look at the capacity of words2. Right, so the capacity of words1 when I had 5 elements was 8 because I had to grow each time, I had to double. But when I made words2, I just said, well, give it an initial capacity of 5, and that was enough to hold all of these strings. And in fact, I'm pretty sure when I did this, I not only gave it a capacity of 5, I gave it a size of 5. Right? So that's a subtle difference. I'm not going to go over all the implications of that right now. I think that would just be confusing. But yeah, so in this case, I initialized it to size 5. What if I didn't do this? So now I'm just going to declare a vector called words2. And to reiterate what we're doing, I'm copying everything from words1 into words2. But I've not like allocated a backing array. And then I'm going to output all of words2 to the console. So printing words1 worked great. I had a capacity of 8. When I tried to copy that into words2, I got a seg fault. Okay, so what happened was this copy function only works if I have room here. So I look at the first location in words1, and as long as there's room to copy everything, then it's going to succeed. But in this case, my capacity is 0 and my size is 0. So this does not work. Okay, so that's one of the things that it's easy to get tripped up on. Because technically I'm not doing a call to push back here, or I'm not doing a call to add. I'm actually copying directly into those locations. But what if I did want to do a call to push back, right? If I wanted this to behave as a normal vector, that is, it's going to keep growing as I add words. That's important sometimes because I don't always know how many words are in words1 in order to properly allocate words2. Or maybe I'm being selective, right? Maybe this stores students, and I only want the students who are passing, and I don't know beforehand how many that is. So what do I do in that case? Well, I can treat this like a regular vector by using the back inserter. So this is a function from the algorithms library. So this is sort of like disguised as an iterator, but what it does is that it calls pushback on words too. So as we add words, it's going to grow as a vector normally would, right? So once again, I'm going to make words one. I'm going to write a bunch of words in it. I'm going to copy those words into words two, but now using the back inserter. And then I'm going to output those words along with the capacity. So there we go. Words one, there are all my words. I have a capacity of 8. Words two, I have all the same words and also a capacity of 8, because now it just grew. It used the pushback function instead of just copying. All right, questions? Okay, what else can we do? Well, this is a vector. I can use an insert. Now, this is like some of the ugliest code possibly in existence, but so I have to call a function on words one called insert, and then I have to call a second function on words one in order to get the parameter to pass to this. It's just bananas. But that's, I mean, I guess one of the side effects of this iterator design pattern. I need an iterator here, so this is how I get one. Well, since this is a vector, these iterators can do pointer arithmetic. So in other words, I'm going to take words one, and then I'm going to take words two, which is just a copy of words one, and I'm going to insert everything from words two into, well, location two, which is the third location. And then I'm going to output words one. All right. Whatever. Okay. So words one with words two inserted. So it says hi there. And then this is location two. And so I've inserted hi there, how are you? And then the rest of words one is here. Okay, so I can insert, in this case, I inserted a bunch of stuff, but I can insert like an arbitrary string. I can insert, for instance, Bob. That will also work. Right, and there we see Bob in the third location in words one. There's also erase, which I'm not going to show you, but it does essentially the same thing, but instead of like, inserting at that location, well, here I'm saying erase everything from location 2 up to location 4, up to not including location 4. So this will erase, starting at location 2, it'll erase 2 elements. All right, so that's basic, some very basic function calls using iterators and algorithms on the vector class. Any questions? Okay. Well, let's look at that same set of operations with the linked list or similar operations. Yeah, let's just jump into it. All right, so now instead of a string, though, I'm going to use my own class. So I've made a student class here. I have a less than operator and a static function, which we'll get to later. But otherwise, it's just a regular, typical student, number, name, major program, GPA. I'm going to make a bunch of students. I'm going to make an output stream and a list. I'm going to push, well, in this case, 4 students onto my linked list, and then I'm going to copy them to the output stream, right? So essentially, I'm adding my students to a list, and then I'm going to print them out, or at least that's the idea. All right, so I have a problem, and maybe a little hard to tell what the problem exactly is, but if we look up here, this seems to be the culprit, right? This gets repeated a lot. So essentially what's happening is the compiler is looking for this operator, right? So I'm trying to send my student objects to the output stream through an iterator, sure, but still to the output stream, and it's looking for the stream insertion operator, which currently I have not implemented. Okay, so yes, we have these fancy iterators and algorithms, but you have to make sure that your classes that you make can handle it. So if I ever want to copy it to an output stream, I need this operator, regardless as if I go through an iterator or not. So yeah, through the magic of uncommenting, there's our new stream insertion. And so now this should work. And there we go. There's our 4 students printed out from our linked list using this copy command. Okay. What else can we do with this? Well, we can sort. Now, there is a sort function that comes in the algorithms library. Here, the linked list gets its own sort function, right? And I'm making an educated guess here. But the reason is that all the sorting algorithms that work well on vectors don't necessarily work well on doubly linked lists, right? Doubly linked lists, if you have random access, you can do different things than you can on a doubly linked list. So this is, I'm guessing, meant to be efficient for a doubly linked list. Incidentally, anybody know which sorting algorithm this would use? Anybody know any sorting algorithm? I mean, not bubble sort. It's definitely not that. Bubble sort is never, ever used, ever in production. It's just a learning tool. Yeah. It's not, but I'm wondering if you could implement quicksort, right? So you got to, there are many different implementations. As far as I know, this is not quicksort. I was thinking about that though. You might be able to do that on a doubly linked list, but they don't, or at least not up to the last time I checked. Any other? So what's I mean, it might be hard. This is actually in 2402. This is I make one of the assignments is to make a doubly linked list, and then to apply this sorting algorithm to it. It's merge sort, right? So merge sort will actually work well on a doubly linked list because you don't need random access. It's easy to split, and then when you merge, you just rearrange some pointers, right? So did somebody in the chat get it? Merge sort, somebody got. All right, yeah. But quicksort, I mean, yes, most things do use quicksort. That's a good guess. I'm not sure if you could implement it for. Probably. All right. Well, we've sorted probably. By default, it's going to look for the less than operator in your class. In this case, my less than operator says alphabetical order by major. All right, so that's, maybe not entirely useful, but sure, let's try it. So we look here, CS comes first, and then geography, math, physics. That does seem to check out. So our list is sorted now. This maybe is not the most useful way to sort things. So maybe we don't want to use this built-in operator. Maybe we want to use our own function. And if we do that, that's fine. We just need to have a certain signature. 1, it has to return a Boolean, right? And 2, it has to take 2 of whatever the thing is that I'm trying to sort as arguments. Now it's flexible. I've passed them by reference here, right? I can pass them by value if I want, or I can pass them by const reference. I just can't pass them by pointer, right? Pointer will confuse the algorithm. So I'm going to just put compare here. Sorry, I'm just thinking, wonder what would happen if we overloaded this function, because I'm only using the name. Interesting. Anyway, we'll come back to that. So if we look at compare, now we're going to sort in alphabetical order by name. Hopefully. And there we go, Amy, Joe, Matilda, Stanley. So that seems to check out. Yeah, so the problem I was thinking of is that I believe I can overload this with I think I can overload it like this, maybe. I don't know, maybe I'm mistaken. And then the compiler should actually be quite confused. Oops. Unresolved overloaded function type. Yeah, what if I don't call it though? Sorry, I'm a little off on my own. Huh. So yeah, there's got to be some method to resolve these, because I am allowed to do this. I'm allowed to make two compare functions, but then down here I'm only putting them in by name instead of signature. So maybe I have to include the signature if I do that. Anyway, C++, man, so much complexity. Let's say I also wanted to sort. Well, I have this compare GPA function in my student class. It's a static function. It goes in increasing order by GPA. So, well, let's try that one. Let's do, this is now in the student class. So I have to use the scope resolution operator, and then there we go. So now if we look at the GPAs, they are in increasing order. Okay, so I can, just because I want to sort does not mean I'm stuck with sorting by the less than operator. I have lots of options, unlimited options for how I can sort things. All right, questions? All right, the other thing is, well, if I want to insert in the third location, right? This is similar to what we did on the vector. On the vector, it was easy. We called insert, said words.begin plus 2. That's the third location. If we tried that with a linked list, right? So now I have this student called Bob. I want to insert at index 2. Well, it doesn't like that. And in fact, it's looking for this plus operator that I've called here, right? Which doesn't exist, at least not for linked list iterators. So like a doubly linked list, if I want to insert at location 2, I've got to walk there, right? I got to start at the beginning and then follow pointers until I get to the correct location. And then I can insert Bob into location 2. It's going to crash. Oh, my internet connection. All right. So yeah, internet connection is unstable. All right, so after you insert Bob, you should then print out the list so that we can see what happens. And there we can see Bob was inserted into this list in location 2, but you know, I have to walk there. So it's not, and that's in general the weakness of linked lists is that if I want to insert in the middle, that's a linear time operation, right? I got to walk there. It's also a linear time operation for a vector because I have to copy things out of the way. And you would think that, well, you might think that the list one was faster, but it's not actually. Strangely enough, linked lists are kind of slow in general. All right. Maybe I don't want to do this, especially if I have a list that's a billion things long, right? I could set up a for loop and then just call that iterator, but they do have a function in the algorithms library to do exactly that, right? I want to advance my iterator twice. Well, this will just kind of do that for you. And there we see, again, we have Bob right in the middle, inserted after Joe. Yeah. So that's linked lists. I still use iterators, but of course I'm limited. I cannot use pointer arithmetic. I cannot use subscript. I have to kind of do things, the slow way. But questions? Okay. Decks, I'm not going to, how much time we got? I'm not going to get into it. I don't think we have enough time. They are random access though, and they are, well, when we have a vector and we want to insert at the front, that takes forever, right? Because we have to move everything out of the way. For a deck, it doesn't actually. I can insert very quickly at the beginning and at the end. Now, C++ does not do decks in this manner. I tried to read what they do, and I don't know. I gave up. They do something really weird. But there is a very simple way to implement the deck, and it's just to keep track of where the first thing is, and then keep track of the size. And then from there, if I want to insert at any index, I can. If I want to insert at the very beginning, I can do that and just move this pointer down. And if I keep inserting at the beginning, I eventually just wrap around, right? So we do like some modulus functions. And anyway, they work really well, especially if I want to store quickly at the front or the back. But we're not gonna get into that. It uses backing arrays, but it uses multiple backing arrays, at least as far as I understood. Anyway, so we're going to look at associative containers. So we talked a little bit about sorting. And so if you have a linked list or even a vector, you can sort things. And then when you insert, I'm pretty sure there's like an insert. Well, you can do a binary search and then insert that way. So you keep things sorted. There might be a function that'll do both of those things for you. Or you can use an associative container, which by default stores things in order. So sorted order. So associative containers use keys. Now, your key might be your value. So your key value is the same thing, or you might have a key value pair, right? So I have a key and I have an associated value, but we sort on the keys. So that gives us set, multi-set, map, multi-map. Well, here is sort of the definitions. A set stores only keys. So the keys are the data, and does not allow duplicates. Whereas a multi-set stores only keys but does allow duplicates. Or you can use maps, which are key value pairs like a dictionary. And so the map is the no duplicate one and the multi-map is the duplicate one. And when we say duplicate, we are talking about duplicate keys. So for these, we have insert, find, lower bound, upper bound. And these are implemented incidentally using binary search trees, right? So these are trees that maintain sorted order, which means things like find will be a log n operation, which is pretty fast, but not quite as fast as a vector. So yeah, the problem is we have some stuff we want to store in sorted order. So let's take a look at that example. In particular, we're going to store students in sorted order. Now, there's a lot going on here, but let's focus first on, well, let's give it the less than operator. So we're going to store them the default order to start with, which is the less than operator. And this will store our students in alphabetical order by name. And So there's our students, and we're going to declare a multi-set of students, and then we're going to insert 5 students and print them out, and they should be printed in sorted order by name, even though I did not insert them in sorted order by name. Okay, and we can see Alice, Bob, Joe, Matilda, Ted. That is indeed sorted order. So yeah, a couple things to note. I did a for each loop here, and I did a const. It has to be const, right? So when I store things in my multi-set, so yeah, I'm discarding the qualifier. It makes them consts so that you cannot change these values, right? So it's going to copy each of those things, as we saw, into our multi-set, and then from there, you're not allowed to modify them inside the multi-set, right? Because otherwise, these are supposed to store in sorted order, and if now I'm allowed to change their names, I'm going to wreck that property, right? So those will no longer be sorted by alphabetical order by name if I'm allowed to change somebody from, you know, Amy to Z or something. Okay, but of course, now I want to maybe sort them in a way that does not use the default operator. So, well, there's a lot going on here. I'm gonna use this compare function, which is going to sort in an increasing order of GPA. And so I'm going to pass this compare function to my multi-set. But it's a templated type, and I also have to tell it, I'm going to compare these 2 students, and I'm going to do it using a function that looks like this, right? This is a type declaration for a function, which we have not really taken yet. If we have time, we'll get to it. Probably we won't get to it. But essentially, this is a Boolean return value. This indicates that it's a function pointer. And then this is the parameter list, right? So the type is a function that takes 2 const student references and returns a Boolean. And then if we do that, well, then we should be able to sort to not declare it twice. We're going to sort them in increasing order of GPA. Okay. Question so far? All right. This is pretty ugly. So in order to make our life easier, there is this, I don't know what that is. Somebody mentioned, because it's not a function, I was thinking maybe like it's a macro or something, but and then I don't know. But whatever it is, I can pass it this function and it returns the type declaration, right? So it returns essentially this. And then we add this to ensure that it's a pointer, right? To tell the compiler that this is a pointer. And then we pass in the compare function the same as we did before. All right, so this is just a shorter way of doing exactly this one. And there we go, still in increasing order of GPA. All right. The last thing we're going to look at is actually maybe the easiest way, but it's kind of complicated. In our student class, we declared this inner class called COMP. It doesn't have to be called COMP. You can call it whatever. It doesn't have to be an inner class. But it is a class, and it overloads the parentheses operator. And the parentheses operator, and then we can overload that. And this is the only operator that allows us to define exactly as many arguments as we want, right? So here I want 2 arguments, and it returns a Boolean. And it's going to sort in reverse order by name. And how it's going to do that is, well, let's keep. I'm going to make an instance of this object, and then I'm going to say if comp, who do we have? Bob and Alice. Bob comes before Alice. Bob comes after Alice. All right, so this is just an object, but because I've overloaded the parentheses, I can treat this like a function, and it returns a Boolean. So here it says Bob comes before Alice, and in reverse alphabetical order, indeed, Bob comes before Alice. So these are called, I believe they're called functors. C++ likes to borrow a lot of math terms. So it's just an object that I can use as a function. All right, questions so far? All right, so one of the easier ways to sort of implement sorting and multi-sort is that I'm just going to pass it a functor in the parameter list of the template. And then I don't even have to pass an instance of that. This multiset will make its own instance of this class and then and use it. So here I can sort in, yeah, I'm going to say it's almost the same as increasing order of GPA, but it is reverse order of alphabetical order by name. All right. So yeah, questions? All right. Boy, oh boy. Finally, let's look at, let's wrap it up here. Oh yeah, container adapters, we'll give them a brief mention. What they are is they really just strip away the functionality of some existing data structure and leave you with a few operations that you want, right? We've implemented one. We made a stack out of a vector by using private inheritance or composition. And they essentially do the same thing. So stack queue or priority queue, you can implement those by default. I believe stack is implemented as a vector by default, but you can ask it to use a doubly linked list instead. Queue uses a deck or a list, and priority queue uses vector or deck. They do not support iterators, all right? So they are sort of limited in that way. All right, so that brings us to algorithms, which is, yeah, we'll do algorithms, and then we'll do the woo clap, and then we'll probably just end there. But algorithms, this is sort of what you need for your assignment or for the tutorial. So algorithms often take as input a pair of iterators, often return an iterator. We get a bunch of functions. Now you're going to find probably that these are not super exciting algorithms. They're easy. You could probably implement them yourself, no problem whatsoever. All right, but they're good to know, I guess. They might come in handy. So again, I have a bunch of students. Now I'm going to use a vector. It doesn't really matter whether I use a vector or a list. I'm going to output those students to the output stream, and then I'm going to sort them. But of course, sorting a vector, vector does not have its own sort function. I have to use the sort function from the algorithms library, and so I'm going to give it, I can't just call sort on it, I have to give it two iterators, the beginning and the end of all of the things that I want sorted. And of course, by default, it's going to do the less than operation, which is alphabetical order by name. Okay, so Matilda, Joe, Stanley, Amy, that is not in alphabetical order. That is before sorting. Sort and then output. All right, before sorting, we have this, and then after sorting, we have Amy, Joe, Matilda, Stanley. Like a doubly linked list, I can pass in my own comparison operator. I'm not sure what this does, but let's see if we can guess. So sorted using, well, now it's student.compare, which looks like decreasing order of GPA. So the highest GPAs are at the top. But yeah, so this sort function works the same as the other sort function, except now we have to pass in a pair of iterators. And technically, I can sort like half of my vector, right? I can just say, roll this, subtract the vector size divided by 2, and then I will just sort the first half of the vector. So I could do weird stuff like that if I like. But let's look at more specifically all of. So this is going to look, I'm going to give it a collection or at least a pair of iterators that is going to look at all the elements in between those two and see if all of them return true for some function, so a predicate, right? So I'm going to say in this case, studvect.begin. Studvect.end. And then I'm going to pass in, well, I have here, so any predicate that I pass in needs to meet this function signature, which is it returns a Boolean, or function type, I guess. Signature is not, it's not quite the correct term. But the return type has to be a Boolean, and it takes a single student as an argument, right? And so it's just going to return true or false based on whether the student passed or not. And then I can say, well, all students passed. Or at least one student failed, right? So if you recall from 1805, the negation of this statement, all students have passed, is that there exists one student who failed, right? So let's see if that works. At least one student failed. So what did pass do? Pass checked to see if your GPA was at least 6.0. And we can see here that Stanley had a 5.6, so Stanley failed. Okay, well, since we are using a vector and it uses random access iterators, I can do, when somebody comes to inspect the school, we sort of sweep the failing student under the rug. And so we're going to we're going to look at all of, but we're going to stop right before Stanley. And then, oh, look at that. If I only look up to Joe, then it says all students passed. So yeah, I can do, I can use my pointer arithmetic there. In a similar vein, I can do the any of function, which is, well, now logically, it's there exists somebody who passed. So here I'm going to say someone passed. And down here, well, the opposite of someone passed is everyone failed. So it says somebody passed, which is true because I looked at everybody and at least 3 people passed. If I wanted to return everyone failed, then I should just look at Stanley. So in this case, I would say, we'll skip the first 3 and just look at Stanley. And then if we just look at Stanley, then everyone failed. Okay. Well, those aren't, again, you can write these algorithms easy yourself. There's also a for each function, which you can also write. This is a lambda, which we do not need. If we have time, we will get to lambdas, but probably we do not have time. But now, for a for each, I just want to pass a function that takes, my vector in this case stores students. So a function that takes a student as an argument and does whatever, doesn't matter. As long as it's a function that takes a student as an argument. In this case, it's going to print the GPA of the student, right? So it's a friend of the student class. So I can sort of map this function to every student in my vector, right? This is sort of, when you get to 3007, you'll write a lot of functions like this. But well, they'll look a lot more elegant than this one. All right, find, so again, simple to implement yourself, right? I believe I asked you to find something on the tutorial. It does ask for an iterator, right? So if you write your own find, you have to somehow stick this into an iterator or something that behaves like an iterator. Or you can just use the find function. And what this is going to do is, well, now we're going to sort of combine these things with operator overloading. So I'm trying to find Joe. Joe is a string. StuVec stores students. So what am I trying to do here? Well, the find uses this equals, the double equals operator. And so I can do it with students, sure. I can pass in a student object and say, is there any student object that matches this? But since I can define my own function for this, I can say, well, also do it with strings. In other words, I'm going to look through all the students, and if anybody's name is Joe, I'm going to return that student. It's going to return true. Right? So I'm going to look for Joe, and then if we find Joe, well, if we don't find Joe, then this iterator will be equal to StuVec.end, which means I looked through every single student, and then I fell off the end of the list. But if it's not equal to StuVec.end, then it must contain something valid, and I'm going to dereference it and print it. And so did we find Joe? Well, yes, we do have a student called Joe, and Joe is in physics with a GPA of 8.3. All right, so we can start to combine these things with operator overloading. Well, here's another example of, well, let's say I want to take every student from my StuVec that is passing and copy it into this StuVec2, which is all the passing students, essentially. So we saw that we could do the copy function, but now we have a copy if. Copy if takes all the same arguments as before. In this case, we're going to use the back inserter because we don't know beforehand how many students are passing, so we cannot pre-allocate this, this vector unless we just made it the same size as this. But that would be sort of inefficient. And then I'm going to pass in this function. Again, it's a predicate. It takes a single student and returns true or false. In this case, again, based on our GPA. So I'm going to copy all those students into StuVec2 and then print those out. Okay, so all passing students, Amy, Matilda, and Joe, and Stanley gets left off here because he's not passing. All right, some other fun stuff is the fill. The fill uses the assignment operator, so I'm saying, well, typically this is a vector of students, so I'm saying from beginning to end, apply assignment to this argument. So by default, I could pass in a student and then make everybody equal to that student. But here I'm going to pass in a string and then overload that operator. And so down here we can see I've overloaded the assignment operator for strings, and I just changed the person's name to that string. So I can call the fill and just change everybody's name to Maddie and then output everybody to the output stream. Right, and now every student is named Maddie. So again, I can take these sort of algorithms and combine them with operator overloading and do lots of interesting stuff, I suppose. Finally, min element. Well, this returns the min element in my range that I give here. Min element is similar to sorting in that we have to be able to compare all students. So I'm going to give it some sort of compare function. If I don't give it a compare function, by default, it uses this less than. The less than gives us alphabetical order by name, which if everybody's named Maddie, that's not going to work very well. So let's comment that out. Woo clap's coming. I need a woo clap alarm. All right, so the minimum student in alphabetical order is Amy, and I print her out. So this, again, returns an iterator. All right, so those are all the things you may possibly need for your tutorial. Questions? All right, none of it's that difficult, but. All right, let's do the woo clap. I'm pretty sure this is the right one. I guess we'll see. So yeah, next class will be exceptions, and then I might wait till next week to release the practice exam because it is based on your assignment, so it might give some stuff away. Not that it's a big deal. I don't know. We'll see. All right, looking pretty stable. Well, the first one's an easy one. What are the three main components of the standard template library? Yeah, and those questions are open to interpretation, but I'm not saying I wouldn't ask this on an exam, but I might try to be a little more specific. Well, we got lots of answers, and it looks like, yeah, most people are choosing one. So yeah, containers, algorithms, and iterators. That's the three main things that we've been talking about. All right. Which of these statements about iterators are true? Select all that apply. Uh, 26. All right, well, let's just start walking through them. They give you access to elements of the container. Yeah, so the linked list, that was the first problem we solved with iterators, is how do we sort of access them in a more general way? We can use iterators. So number one. Number two, they allow you to interact with a container in a consistent manner. Again, since the syntax is the same across containers, it does allow that. We can run algorithms just on iterators without worrying necessarily about the containers. They are an abstraction layer between containers and algorithms. Well, yes. So all three of these could be considered true. As long as you selected anything, you should be good. Okay. What is this now? Assume we have a list of ints. Want to insert the number 3 into location 3. What is the correct way to do this? Select all that apply. Yes, so. Oh yeah, we didn't really show this, eh? But you can do that. I could take an iterator and then just, if I take the subscript at 0, it gives me back whatever that's pointing to, or I can take subscript at 1. So I can treat any individual iterator as an array starting at that location. But of course, that is a subscript operator, so let's see what people are saying. Lots of stuff, but I guess the key to remember is that this is a list, which is a doubly linked list, which means that this is a pointer arithmetic, which we cannot do on a linked list iterator. This would work on a vector. This would also work on a vector. Yeah, I believe it would do the exact same thing as this. Although we didn't actually look at this, but this would be the way that we could do it on a doubly linked list. We have to manually advance the iterator or call the advanced function and then insert there. So number 2 would be correct for that. We want to insert the number 3 into location. Oh, we have a vector. I may have given away some of this stuff, but so yeah, same question now with a vector. I mean, I think I told you guys the answers. So yes, of course, this should work on a vector. This should also work on a vector, although we did not do it. To the best of my recollection, it works. You know, the language is always evolving, so better to check that stuff out than to believe me, but this also would work on a vector, right? We're allowed to use, this is not efficient, but it would work. So 1, 2, and 3 are all valid answers. All right, I'll wait a second for. All right. Now, yes. What is the output of the following code? So we've defined this function sort of inline. We have an output stream iterator. We've got an initializer list, which if you're working in C++ 11 or higher, which I don't explicitly state that we should do this, but you should do this. Everything sort of depends on C++ 11. So what does this print out? Geez, that's a bit of a tough one, eh? So I'm going from numbers.begin to numbers.n minus 1. So I'm looking at the numbers 1 through 5. And then I'm copying them to the output stream, but only if this function returns true. It returns true if the number is even. So if we look at the answers, yeah, it should be number 3, 2, 4. We don't quite get to 6 because of the little bit of pointer arithmetic. All right, I think that's it. Yeah, questions on any of these? Okay, well, we'll stop there for today. So next class, we will take exceptions, which do appear on your final exam. I will give you plenty of hints about what exactly you should expect. But yeah, see you guys in a couple days. Yes, but not all of it. So just the simpler stuff like you should know how iterators work on vectors and linked lists and say how to write a for loop and stuff like that. But the algorithms, you don't, I don't think we do any of those. That's more for your tutorial.